It's now 10:30. Welcome back, everyone. We apologize for this technical issue, but we are very pleased to have Soroush now. And the structure of the session, we have 1 hour. Soroush will give a talk as we planned. We open up a discussion Q&A straightforward, and then we finish 11:30. Again, we apologize this technical issue. And I want to pass the floor to Soroush. Soroush, can you please start your talk?
Yeah, I can do that. Let me, I need permission to share my screen, though I don't have permission to share my screen.
Okay, I'll have to stop sharing.
All right. So thanks for the invite, and I want to talk to you today about this topic of machine learning and public policy. So I teach a large class at Harvard on machine learning and big data analytics, and so we cover a lot of algorithms, and we talk about the details of the algorithms and the technical side of algorithms and how they work and how they learn. But we also cover a lot of examples of how they've been, applied to solve the public policy issues that we have. So in recent years, these algorithms have been used to help us to rethink some of the public policy issues that we have. And so today I would like to share some of those examples with you. I always start my class with raising and answering this question, and I would like to do the same thing today, which is, why is machine learning becoming really important? So I provide 4 answers to this important question. I don't have the time today to go through all those 4 answers, but the one answer that I would like to share is this, that many of the policy questions can be answered these days with machine learning. Here's, for instance, one example: are police begetted? Are blacks targeted more? So you may have heard a lot of politicians and policymakers sitting around and just arguing about their opinion, while we have these fantastic algorithms as well as huge amount of data that we can give to these algorithms to make sense of the data for us. So organizations, as you may know, are becoming more and more data-driven. So titles like CDO, which is the Chief Data Officer, doubled from 2012 to 2014. There's a survey of about 1,300 companies worldwide. That survey shows that over half of companies are using analytics in everyday decision-making. There is a survey that was done by MIT a few years ago. This is of a survey of 333 public American companies. And it shows that companies that are in top third of their industry in terms of data-driven decision-making, these companies are usually 5% more productive and 6% more profitable than their competitors. But this is not just happening in private or public companies. We are seeing a lot of use of machine learning algorithms these days in the government as well. So here's, for instance, one example in the US. The Santa Cruz Police Department in California is using machine learning techniques, some of the algorithms that I teach in my class, to do what we call predictive policing, which is the approach essentially that they use is this: to identify parts of the cities that are at high risk of crime. So you can use a lot of this machine learning and predictive analytics to do this. But the advantage is that once you do that, then you can share that information with the officers, and you can use the limited officers that you have much more efficiently. So I want to also talk a little bit about this article from The Economist, which to me talks about an important, raise an important question, which is this, which is that, is it time to automate politicians? Are we ready to have all these machine learning algorithms be built in robots, along with data sets, and have them be our politicians? Now, why do I think that's an important question? The reason is because we know from a lot of research that big data and AI is enabling us to make better decisions. they did actually a poll of British consumers, and they found that 1 in 4 Brits think that robots would do a much better job than humans as politicians. Now, I don't know how much of this was impacted by the issues in the UK, including Brexit and others. But the fact is that these things are becoming more and more real. In 2018, for instance, in April, a robot was nominated to be the Tokyo's mayor, actually. And so, you know, all the nominees have plans. Like you can ask them questions. You could ask, like, what is your plan for reducing the traffic in Tokyo? Every nominee has a plan, and so does the robot. It has gone through large amount of data. It's using a lot of advanced algorithms to be able to answer those questions. So I would like to urge you to think about this question. And the question is this: do you think robots would do a better job than humans as politicians, let's say in the next couple of decades? Are we going to have robots that can be essentially working as our politicians? Now, I want to also mention the fact that policymaking typically involves complicated decision making. And machine learning and AI techniques have made great progress in this regard. So here's, for instance, one example, and some of you may know about this. So this came out of the DeepMind group, and a few years ago in Nature, they published this paper. They used some of these techniques that I teach in my class, including reinforcement learning. And using those techniques, they were able to beat the best human player in a very complex game called Game of Go. So for those of you that are not familiar with the Game of Go, it's a very complex game. You have to think about many scenarios, and each move that you make, you have to think about the consequences that it has down the road. And so they were able to use these algorithms to beat the best human player, but that's not the important thing. The important thing is that they were able to do it in a tabula rasa way, which means that they were able to do it starting from scratch. So if you think about the previous AI and machine learning techniques that we had, we would usually give a data set to the algorithm, and we would train the algorithm over that data set, and so the algorithm then is trained and can make decisions. But this is different, and if you do it in this way using tabula rasa techniques, what it means is that now you don't need to have any human generated data, right? So you have algorithms that are not learning from human generated data, and the advantage is that you can remove when it comes to solving some of the societal problems that we have. For instance, you can remove the biases that we have in data sets that are typically generated because the data is created by a human. And so now we have the ability to have AI agents actually create their own data and try to learn from their own data, as opposed to being trained on data sets that are generated from by human being, and those data sets are usually biased, as I mentioned. So what I would like you to think about is this: can these advancements help us make better policies to resolve some of the lingering societal problems that we have? What does it mean now that we have these advanced techniques? What does it mean for us to be able to solve some of the societal problems that we have not been able to solve previously? I want to also mention that it's not just that these algorithms are enabling us to make better decisions, which is fundamental for being able to solve some of our societal problems, but is that they are also enabling us to understand our own ways of our own ways of decision making. So as humans, how are we making decisions? What are the type of rules that we follow as humans to make decisions? So here's one example that was published in Science from Tom Griffith's group. He's a psychologist at Princeton, and they use this deep learning techniques and neural networks essentially to go through large amounts of data of how humans are making decisions and try to make sense of it and try to figure out sort of the fundamental theories behind how humans make decisions. So for instance, are we following what prospect theory predicts, or are we doing things differently? So again, the advantage of these algorithms is not just that they are enabling us to make better decisions, but that they are also enabling us to understand our own ways of decision making and how we make decisions. I want to talk a little bit also about IBM Watson. And so in 2005, a team at IBM Research started developing a computer that could compete in a game that is very popular called Jeopardy. And no one at the time could think of even beating human players in a very complex game like Jeopardy. Now, 6 days later in 2011, a 2-game exhibition was matched on TV, or was aired on TV. The winner would receive $1 million, the second place would receive $300,000, and the third place $200,000. Now, who are the contestants? Well, these are the players. So we had Ken Jennings. He was the longest winning, he had the longest winning streak at the time, 74 games was the streak. So about half a year of the show. So 74 games is about half a year of the show. Then there's Brad Reuter. This is the biggest, he was at the time the biggest money winner, over $3 million at the time. He had never lost to any human player in Jeopardy. So these are, we can think of these two players as sort of the extraordinary players that we've ever had in very complex game like Jeopardy. And then the third participant is Watson. It's a computer with 3,000 processors essentially and a lot of data sets. Now, you may know that this wasn't the first experience that IBM was doing. So, you know, in late 80s and in 90s, they developed Deep Blue, which was later in 1997, it was able to beat Garry Kasparov in chess. So this wasn't the first experience that IBM had. But let me show you how, for the Jeopardy, how IBM Watson was able to make progress. So what I have here on the x-axis, I have the percentage of questions that are answered. So in Jeopardy, there's a question, and you can decide whether you want to answer the question or not. Typically, what happens is that the more question you try to answer, your precision, which is the y-axis here, that decreases. So ideally, where you want to be on this graph is on this northeast corner, but it's very difficult to get there. You can see that this is where IBM Watson started. This was in 2007, and they made progress. So what are these dots here? Let me tell you a little bit about these dots. So the lighter dots, these are human winners. These are typical human players that are good and they win. And the darker dots, these are related to Ken Jennings, who was, as I mentioned, never lost to a human player. So Ken Jennings is extraordinary, and if you and I play in this game, we are going to be somewhere most likely here. Now in 2010, you can see this was where IBM was in 2010, was able to get close to Ken Jennings, and this is the final result of what happened. IBM Watson was able to beat both Ken Jennings and Brad Reuter by large margin. Now, the reason I'm mentioning this is not because IBM Watson was able to beat, these two extraordinary human players, but more because it's being used in a lot of different industries, and it's trying to, solve some of the societal problems that we have. So, for instance, it's being used in healthcare for medical diagnosis. So as some of you may know, diagnostic errors in healthcare, that's the sort of the main contributor to malpractices. And they cost us about, on average, $300,000 per claim. Now, IBM Watson has been able to reduce malpractices by a good margin. And the reason that it's able to do this is because, it's trained on huge amount of data. We have, electronic medical records. We have medical textbooks and literature. We have more than 5,000 diagnostic questions from the American College of Physicians, Dr. Dilemma of Competition, for instance. So IBM Watson has gone through all this data set and, text and other things that we have, and it's been trained on this. So you can do a lot of good things. Now, you can imagine that in near future, we can go to IBM Watson and even ask these types of questions: how to reduce inequality, how to solve looming debt crisis, and how to decrease healthcare expenditure, how to make education more affordable. These are some of our lingering societal problems, and I think IBM Watson in near future can answer this. The reason I'm optimistic about this is because I know that we have huge amount of data on each of these questions. There is huge literature on each of these questions, several papers, books, studies that are available, and we know that the algorithms that we have are able to be trained on these data sets to make better decisions. Now, IBM Watson was sold to a private equity company a few months ago, but that was more for financial reasons. That wasn't because of its potential. What I want to do for the rest of the talk is this, that I want to give you some examples of how machine learning techniques are being used to solve some of the bigger problems that we have in our societies. Some of the examples that I will give you are from my own lab and from my own research group. Some of them are from other groups, and we're going to go through them to give you some examples. So the first one is about healthcare. That is from my own group and from the research that we did a few years ago. So as a lot of you may know, in healthcare, the healthcare in the US is having a lot of problems. We are spending about 20% of the GDP in healthcare in the US. And that's, if you compare, for instance, the per capita spending in healthcare in the US, that's about 2.5 times other developed countries. So we're spending a lot in healthcare in the US. And or outcomes, quality measures and other things are not also comparably, they are not comparable to other developed countries. We're doing much worse in terms of the quality that we have, but we are spending a lot. So obviously there are several issues in the healthcare sector, but one of the things is that we don't know which type of physicians are actually doing okay. So we don't know who is an effective and efficient physician, for instance. And so without knowing that, there's no way to improve what physicians are doing. First, you have to understand what physicians are doing good and what physicians are not good. So we try to do that. We ask, algorithms, this machine learning and AI algorithms, to go through huge amount of data sets that we had about how physicians are delivering care, the patterns of their practices and things like that. And we try to ask the algorithms to make sense of what they are doing and tell us essentially who is a good physician. And the importance of that is that once you do that, you have the ability to go to the physicians that are not good. And then you can tell them that if you want to be an effective or an efficient physician, these are the type of things, for instance, that you should do to be a good physician. So for instance, we used DEA along with several unsupervised learning, machine learning algorithms. And what we wanted to do essentially at the end of the day was this: we wanted the algorithms to assign each physician to one of these four groups. So group one is the group that is high on effectiveness and high on efficiency. Group number two is, are the physicians that are high on efficiency but low on effectiveness, and so on and so forth. So we wanted the algorithms to learn and assign each physician to one of these four groups. And obviously, once you do that, then you can go to the physicians that are not in group one and tell them, if you want to, move to group one, these are the type of things, these are the type of changes that you need to make. So we used several, data sets and several algorithms. So for instance, here you see what happens when we use k-means clustering, for instance. We also use random forest clustering and other techniques. You get similar sort of answers from algorithms. And again, here, the importance is that you can improve what physicians are doing. I want to talk also about sort of understanding the crime data and what happens in terms of crime rates in different countries. And specifically in the US, there's a data set called US arrest data set. So in the data set, you have a lot of information. So you have number of arrests per 100,000 residents for things like assault, murder, rape, and you have this data for each of the states separately. And you have, other things about states as well, like what's the percentage of urban populations, so on and so forth. If I want to show you just a small picture of the whole data, you can see here that we have, for each state, we have different information. This is a high dimensional data set, and obviously, it's very hard to make sense of high dimensional data sets. Intuition typically fails in this data sets where the dimensionality is high. And I always tell my students that I think, Einstein was the only one who I know of who could think in 4 dimensions. Most of us fail in 3 dimensions. But the advantage of some of these machine learning algorithms that we have is that they can reduce the dimensionality of the data set to something that we can understand, and then we can make sense of it. So even simple questions like, if you want to understand whether when it comes to crime, for instance, Arizona is closer to California or let's say to New York. With this high dimensional data sets, even simple intuitive questions like that, we are not able to answer them. But with this machine learning algorithms that we have that allow us to reduce the dimensionality of the data set to something that we can understand. We have a lot of algorithms in AI and machine learning that, as you know, they work more like black boxes, and it's very hard to go to policymakers and try to communicate what's happening to them if the algorithm is completely a black box. So we need explainable algorithm, and we need to do things that can be described to human decision makers like policymakers or people in the government. But with these algorithms that I mentioned, so for instance, here we have PCA, where we are trying to reduce the dimensionality of the data set to 2 dimensions, so we can see what's happening and we can answer questions like the question that I asked you. So if you look at here, for instance, you see when it comes to crime, New York is much closer to Arizona than California. But not only that, now you see that some states are doing okay in terms of crime and some states are not. So for instance, you can see Maine is doing okay in terms of the crime. And if you can now go to the governor of Arizona and say, hey, if you want to be more like Maine, these are the type of changes that you need to make in your state to be able to, get to closer to Maine in terms of crime. I want to also talk a little bit about how this machine learning techniques are enabling us to change some of the policies that we have surrounding how we screen for different diseases. For instance, this is related to breast cancer. And what we have here with genomic data, we are now able to make changes and make these policies be completely personalized. So a lot of screening policies that we have in the US and around the world, they are not personalized because we don't know how to understand the subtypes of diseases. But with this machine learning algorithms and huge amount of genetic data that is out there now, we are able to make these policies personalized. So for instance, what you see here is that on each row, I have a gene, and on each column, there is a person. And so lots of people, but also lots of genes for each person. So with this machine learning algorithms, now we can understand the subtypes of breast cancer. So here's hierarchical clustering. For instance, the genes that are here that you see, they're red. These are the genes that are active. So they are expressing themselves. And so we can, this was done actually in Stanford, by the way. We can understand that when these types of genes are active, this is related to this type of breast cancer, which is called luminal subtype A. So with this machine learning algorithms, now we have the ability to make the screening policies that we have a lot more personalized and get to the subtype of sort of diseases rather than just to try to treat or try to have a screening policy for the general disease. Another example that I want to talk to you is about learning how people vote and what makes people vote for one candidate versus the other candidates, and how counties, for instance, in the US vote for one candidate to the other. So suppose you are in April of 2008, for instance. At that time, if you remember, the momentum of Hillary Clinton was picking up. So people were thinking whether she would win against Obama. So at that time, we had access to machine learning algorithms. There were a large amount of data sets that was also available, and we could use this machine learning algorithms at the time to understand what it makes people to vote for Obama versus Clinton, for instance, right? And understand that how counties vote differently to different people. So the data set that was available there, this is the data set of all the counties in which the primaries, this is how the elections in the US work, the primaries were done. The data set included the following variables. So you had a lot of demographic measures, things like age, ethnic makeup, education, etc. You had a lot of political measures, things like whether the county in previous years, in 2004, essentially voted for George Bush versus Kerry. you have a lot of economic measures as well. So what is the unemployment rate in that county? What's the amount of construction going on in that county? And a lot of other economic measures that, we have for each of the counties. So, one simple question is this: given all of this, potential predictors, for instance, one explains the county level voting. Which one explains the county level voting most? And if you use some of these machine learning techniques, for instance, what we call it recursive binary splitting, you see that the most important variables is percentage African American. So not only that, but it also gives you an optimal threshold. So you have a simple rule now like this, which says if the county has more than 20% African American, then they will vote for Obama. Otherwise, they will vote for Clinton. But you make use of this binary splitting, recursive binary splitting, to get better predictions and to get closer to actual reality of how people are voting for one candidate versus the other candidate. So if you do that, you get pictures like this that are not only doing a good job in terms of their the predicting what happens, but also they are very good in terms of interpretation. So these are very easy to understand. I'll show you what it's essentially showing. If I zoom a little bit, I can show you. So the first question, for instance, is what I showed you, whether there's more than 20% African American or not. And if the answer is no, then there's another question. The question is related to high school graduation rates. It's essentially education. Is the high school graduation rate higher than 78%? Yes or no? If the answer is no, the algorithm predicts that the county will vote for Clinton. If yes, then there are other questions. And you see here that then it gets to the household measures and whether, for instance, where the county is it in north or south or west or midwest and things like that. As I mentioned, now, this is not just enabling us to understand how people are voting for one candidate versus the other candidate, but also that, these are very good in terms of, predicting, in terms of interpretability. So this was actually put on New York Times. Anybody who can read New York Times can now read this and understand what is happening. These are important when, we want to communicate some of these results to the general population, as well as to the policymakers. We need really algorithms that are good in terms of, interpretability. Another example I want to talk to you about is trying to predict what happens in Supreme Court. So the US legal system, as some of you may know, is an interesting legal system where you have the Supreme Court at the top, where all the difficult, but also most important in terms of like their societal impact, the most important cases go through the Supreme Court. And so here, what researchers did, they tried to use some algorithms to predict what happens when a case goes through the Supreme Court, right? So the decisions that are made are typically a justice there can vote to reverse the lower court decision, or they can affirm it. So let's say 1 for reverse and 0 for affirming. And what the researchers did here, which was interesting, was that they also asked a lot of legal experts. So these are really good law professors and others that are very close to understanding how Supreme Court works and how justices vote for different cases. They also asked the human experts to make predictions, and they put all their predictions online before the cases go through the Supreme Court. And so with that, they were able to compare what human experts predict versus what the machine learning algorithms are able to do and predict. Not only that, but the machine learning algorithms are able to extract pattern and try to understand what makes the justice, reverse the case or affirm it. So for instance, one of the justices at the time was Justice O'Connor. And this is what the machine learning has learned by going through the cases and by going through all the cases where Justice O'Connor has voted for, and is now trying to represent how Justice O'Connor is making decisions by this very simple tree. So for instance, is the lower court decision liberal? If yes, then the algorithm is predicting that Justice O'Connor will reverse it. If no, then there are other questions. The case from the second or third DC or federal circuit court, yes or no, and then based on another question, it makes the final decision. So this is, the algorithm has gone through the data set and is now trying to represent what Justice O'Connor does in the best way. So it's not that we have written a bunch of if-thens and say, for the algorithm what to do. It's just that we have given the data set to the computer along with some learning algorithms, and using those learning algorithms, the computer is able to extract these patterns of decision making. So let me show you the results of how the predictions worked for this specific case. So in terms of the accuracy of the machine learning models, the accuracy of, this is for the overall case prediction, was 75%. The experts' accuracy, these are the human experts, although they were really well-known law professors and people who are really close to the Supreme Court and understanding the Supreme Court. That's their own study and branch of work is in that area. Their prediction was about 59% accurate. So the machine learning models worked much better than what human experts could do. When it comes to individual justice predictions, this is the predictions of each of individual justices. The models and the experts were very close, so there's not much difference here. But in terms of the overall prediction, you see that the the machine learning models did much better than the human experts. Okay, so the other example that I have here is what I teach in my class. This is about the whole area of misinformation and creating fake speeches and things like that, which is now becoming a big deal, unfortunately. So we cover this case, and my students learn how to make a fake speech of President Obama using some recurrent neural networks, essentially. And when we show the students what the final result is, they cannot tell that the result is fake. So previous techniques, so these are the techniques that were available in 2016, for instance. When you look at them, you could say that, this is fake speech, something is wrong with this speech. But with the newer speech, which is this type of a speech, so there's a video of this, I'm just showing you a snapshot of this. With the newer techniques, you can even tell that the speech is fake. And so that's how much the technology and this machine learning algorithms have improved in terms of like being able to replicate things. But this is a very dangerous area because you can create complete fake speeches. You can give text, you can write the text of the speech and just have the machine learning algorithm create a completely fake speech based on the text that, for instance, you wrote. And the other example that I have is again from my own work with my research team. And this is what we wanted to do here. We wanted to sort of understand what makes startups successful and what policymakers should do to make the startup ecosystem essentially productive. And so the first steps that we took here, we gave a lot of data set, a lot of information about many startups. Some of them have been successful, some of them not. And these are not the startups in the US, these are startups all around the world. And we asked our machine learning algorithms essentially to tell us what makes this machine learning, what makes some startups successful and some others not, what makes them to have high, what we call it, post-money valuation and things like that. But so I put the reference here. I'm happy to share that with you. These are all also available on my website. If you go to my website, you can find them. The last example that I have here for you is about the fact that these machine learning algorithms are also enabling us to predict civil wars. So if you think about the previous literature in the civil wars, and again, I want to emphasize that this is not just that the machine learning algorithms are enabling us to predict things like, predicting, for instance, civil wars here in this specific case, but they also enable us to understand what drives civil wars. Specifically in this case, if you know about the literature on civil wars, the longest standing literature suggested that, civil wars are essentially driven by collective grievances that are stemming from ethnic diversity and or income inequality. So the whole literature that we had before using this machine learning techniques on civil wars is essentially summarized here, that they are driven by collective grievances which are typically stemmed from ethnic diversity and or income inequality. When you use machine learning techniques, now you get a different picture. Newer techniques give you a completely different pictures. They show you that civil wars are essentially largely driven by the opportunity for insurgency. So what it means is that interstate conflicts essentially emerge in states that are not strong enough to control potential rebellious groups, and where such groups can essentially thrive. So you get, again, my point here is that you get a different picture about what is driving civil wars. And it's not just that you have now the ability to predict them, but you also get a better picture of what drives civil wars. And so the algorithms here perform relatively well. Here, what we have is in terms of their area under the curve. I'm not going to go through that, but again, the point here is that they work really well. Not only that they, in terms of the prediction again, but also that they allow us to get a more accurate picture of what drives civil wars. So with that, let me conclude, and then I'll open it to if there are questions. So in conclusions, I believe that machine learning and big data analytics is becoming increasingly important, specifically when it comes to public policy. Big data means data availability is increasing. Data is influencing how we are understanding things, and increasingly is driving policy decisions. A lot of policy decisions are now being driven by use of AI and machine learning techniques, and I think there's a huge opportunity here for researchers to jump in and to try to influence how many of our public policies are made. I want to emphasize again that many of the public policy issues require dealing with complex decisions. The decision making there is very, very complex. You need to think about several consequences of any of the policies that you impose. Some of them will hurt some people, will benefit some others, and so you have to have really complex understanding of what their consequences. But machine learning and big data analytics, I believe that here they play an important role here, that they can influence how we do these things and how some of our most important public policy issues are made. We no longer need to rely on human data, which is an important factor here. As I showed you, now with some of the newer techniques, we have the ability to have AI agents essentially generate their own data and learn from that, as opposed to relying on human-generated data. Human-generated data is typically biased, has a lot of issues, and so when we train algorithms on human-generated data, obviously, the algorithm will have those issues as well. But with newer techniques, we now have the opportunity to do something else, do something that doesn't result in algorithms that are biased. So I hope I have influenced you to learn more and hopefully use some of these machine learning algorithms that some of you may know on trying to solve some of the important policy issues that we have and some of our lingering societal issues. So with that, I'll stop here. I'm happy to answer any questions you might have.
Thank you very much, Soroush. Thank you very much, Professor Saghafian, for a great presentation, very interesting examples. So we have, as I understand, about 22 minutes, according to the previous plan. We lost some time. Again, apologies for that. But, I'm sure we will have a great time here. Now, questions. Let me first ask a question from our panelists. Professor Robert Kohn from the UNSW. Robert?
Thanks very much. That was a great talk. Now, there's in some areas, you can just like Go and chess, you can just train the machine to get better and better, more correct answers. But in some areas, you probably need subject matter knowledge as well. And so the question is, how does subject matter knowledge versus machine learning interplay? In particular, can we just give the machine access to lots of books and articles and replace subject matter knowledge, or is intuition behind subject matter knowledge so important that in some areas you will never have more than, you will just need to have a partnership. In particular, I'm thinking about the Supreme Court case. You showed us machines versus experts, but you didn't show us machine plus expert.
Yep. Yeah, so that's a very good question. And so that's the area where we call it centers, essentially, center decision making. Centers are half human, half machines. And so that's the idea there, is to combine humans with machines. And there's a good amount of research going on showing, for instance, for playing chess, we know that centers, you know, they work better than either machines or than human players. And I think the answer to your question depends on some areas, some applications. I think for playing, you know, if you're thinking about playing bridge, for instance, you know, you can have just a machine that works better than any human player. And probably if you combine it with human experts, in other words, if you use a center sort of model versus the machine learning only model, you won't get that much benefit but for some of this, you know, solving some of the societal problems, I believe the combination is needed, and a lot of, you know, work that we do is aligned that line of having a decision support system. The decision support system gives sort of, you know, the recommendation to the human interacts with that recommendation. And that is also used as a feedback loop for learning. So a lot of projects that I have right now, we have this combined model of human expert plus machine learning. And we see that, you know, they typically work better in long run compared to using either, you know, the machine learning models or human generated data. So I think that the answer depends on application, but in a lot of applications, we are seeing that this, you know, what I call center models of decision making is better than human decision making, and is better than only you know, AI decision making.
Okay, thanks. A follow-up question is, when it comes to policy and when it comes to self-driving cars, for example, you've got to make an ethical decision, and it's not just a clear conclusion. You know, in self-driving cars, for example, the machine has to make a choice between, for example, killing the driver and swerving off the road, or killing 3 other people by driving on. And there's no clear answer to this. In the same way, say, in the current Ukraine war, if you were the US, or if you were the US, for example, you'd say, what are the trade-offs between putting American boots on the ground versus not doing it? And there's no clear answer. And in those situations, like self-driving cars, or even allocating funds for things, you know, it's very rarely that you're going to get the case where by a particular decision, you're going to have everybody better off.
That's right. Mm-hmm.
So how do you tackle that?
Yeah, so that's a good question. And we have, you know, in the class that I teach, we have quite a few sessions on these types of decision making. So the first thing to notice is to compare it with what is happening right now. Is that, you know, a lot of these things, we have a human decision maker that is, or a human policy maker is making decisions, right? So how do they do that, right? So and are we able to do better considering all the aspects of things? But one of the, when it comes to using this AI techniques and machine learning techniques, one of the main things that we talk a lot in my class is about the objective function. And the objective function needs to include, the ethical issues that you're talking about, needs to include them correctly. And that's, different than a lot of applications that we see in computer science, for instance, where the objective function is completely clear. If you're playing, the game of Go, you want to win the game, and the rules, everything is clear. In public policy, those things are not clear. So you need to have, extensions of AI and machine learning where you can play with in this, what I call them, games without clear objectives. You need to have that. And ethical issues here are extremely important, right? So there has been a good amount of progress made in the last 10 years about, including ethical issues into the objective functions. But that's still, a very active area of research is doing that. I can give you one quick example about one of the projects that we recently had, which is, Mass General Hospital is one of the leading hospitals in the US. They asked us to develop an algorithm to assign they have a new technology for treating cancer, which is called proton therapy. And they wanted us to develop an algorithm that can assign their limited capacity that they have to patients who apply for it. So almost everybody who has cancer and needs to get treatment now wants to use this new technology as opposed to previous technology, which is X-ray based. And so we needed to develop an algorithm that can, when people want to use this technology, they apply to use it essentially. The algorithm either accepts them or rejects them. Obviously, it cannot accept all people because the capacity is limited. So there are, ethical issues here is that, the algorithm can predict how much benefit they can get. And if there is a person who's, 101 years old, the algorithm predicts that they are going to die either way, whether they get this technology or not, right? Versus when a kid, the 2-year-old kid, is applying to get this technology, the algorithm predicts that it's going to, have a long-term effect on the life of that person. But then the ethical question is that, is it ethical for the algorithm to deny treatment because it can predict that that person is going to die either way, right? So that's an ethical issue that, for instance, in one of the projects we have worked with being, tackling. And these are, as you say correctly, Robert, they are much more complex than some of the, traditional applications of AI and machine learning.
Thank you very much. On a follow-up question, Valentin, tell me when I've asked too many questions, but on a follow-up question, it seems to me that a big area is, of course, just training recurrent neural nets and that sort of stuff. But another area that I think is important is the area of causal inference and how we can train machines to actually be smart about causal inference. Because in traditional stuff like chess, etc., you feed them the machine lots of games, lots of situations, and you basically, the bigger the database, the better it is. But in causal inference, you've got a situation where things are in a particular way for a while, and then something changes, and without thinking hard about it, the machine will assume that things will just go on the same way.
Right.
So how do you incorporate causal inference into the whole flow, algorithmic flow?
Yeah, absolutely. So one of the most important, I would say, areas that my lab and myself have been working on is the area of causal inference in AI. And the reason is because we very specifically when it comes to policies, you need to understand the causal effect of the policy. So when we recommend the policy, it's not just because it has a predicted good way, but to predict it correctly, you need to actually predict the causal impact of that. So I do a lot of work in causal reinforcement learning, and a lot of these policies that we try to develop in our lab, they are based on these methods that enable us to understand the causal impact of policies. Because otherwise, what you're recommending is not correct, right? So because you can recommend a policy without being able to estimate its causal impact. If I'm saying the policymakers are doing X, they should do Y. Well, I need to be able to first estimate the causal impact of doing Y versus X, right? So you are absolutely correct that because we do a lot of these things for policymakers and to recommend policies, we need to be able to understand their causal impact, and that's an area that we are working on, and obviously there has been a lot of work from other groups as well.
Okay, just to Valentine, do you want me to stop now?
I would want to thank Professor Saghafian and also pass the word to Tomohiro so he could ask something.
Okay.
Don't mind.
Thank you. First of all, thank you very much, Soroush. It's a fascinating talk and so many insights. And before I just bring my question, we got a question from Paul. It is, thank you, Professor Saghafian, for the inspiring talk. I'm quite interested in your mentioned paper, in which I noticed that efficiency score of efficient estimated by DEA is further validated and analyzed with various machine learning algorithms. May I ask for more advice on effective models for this purpose, based on your experience, please?
Yeah, of course. So, again, I'm happy to share the papers also on my website. But what we do here, we can think of developing essentially a score for how good, in this case, was physicians, but you can do that in different industries. It doesn't need to be, for physicians, you can do that with any of your colleagues, even like, if they're professors or researchers or whatever their job is. You can develop these algorithms that try to essentially give a score to their effectiveness as well as the efficiency, right? And then once you have those scores, you have the ability to use what we use unsupervised machine learning to try to cluster physicians into the groups, but you can do a lot more in that area as well. And I'm happy to again share the paper.
Thank you. Another question from Paul. Thank you for your thought-provoking talk. I'm quite a lot of major public policy matters. It isn't the fact that we do not know policy solutions, but the policy is political. How do you think AI machine learning identified policy solution would be treated differently by policymakers than traditional policy advice?
Yeah, so so that's a very good question. And the way I think about this is in two levels, is that, when there's difference in implementation versus finding the best policy. And so there are two levels. You first find the best policy and you can recommend it to the policymakers, but whether they implement it or not, in other words, whether they follow it or not, then there is the political power, there are, political stuff that is going on. And that part, we don't have control, of course, over it. If the president is from Republican or you're at the time where the president is from the Democratic group, the outcomes are going to be different. But that's the second level. It's just in terms of implementation, whether they follow it or not, that's on their side. But in terms of finding the best policy, I think AI and machine learning here can do a lot. And what I've seen over the years is that I think policymakers are becoming more and more open to getting suggestions that come from rigorous machine learning techniques. There are some machine learning techniques that are not rigorous, or sometimes they are not explainables. And so if the policymakers cannot understand what's going on and how the algorithm came with that recommendation, they're not going to follow it. But once you do a good job of using the right set of tools, what I've noticed is that they are open. They listen, and they listen more than traditional advice, because the traditional advice comes from human beings, which have cognitive limitations. We know that all human beings have cognitive limitations, and so policymakers know that as well. They know that recommendations that come from machine learning and AI techniques can be much more effective, much more, there are better solutions in many areas. But in terms of implementation, again, that's a different story, which that depends on who's in charge and what their political views is, what their political power is, what their goals are, and all sort of things.
Thank you very much. Yeah, so this is from me. If you look at the government, there are so many areas they can potentially utilize AI, machine learning. From their perspective, there are so many choices. When they choose AI project or nurturing a capability of AI, then implement and embedded some capabilities into their routine. And any recommendation for policymakers or managers, which area they have to invest, which area they do not. Any sort of guideline recommendations to the government? It applies to Australian government and even government everywhere, I believe.
Yeah, I think there's a lot of there's right now in the US, I can tell you, because I know the situation in the US better than other countries. But in the US, there is a lot of improvement in how mayors and how cities are thinking about using AI. So the White House has now a department that is essentially dedicated to use of data and AI. And so a lot of mayors, a lot of cities, governors of different states, they're thinking of using these techniques. And so I think that's the area in terms of city management and obviously healthcare, which most of my work is a big deal, but also in education and in other areas. And I think if I want to answer your question, it is where decision making is complex. That is where I think AI can have the most powerful impact. And so complicated decision making is where we need most. We need AI most.
Thank you very much.
Thank you, Soroush. So if I may ask maybe the last questions, we're running out of time. When Tomohiro was courageously solving the AI issues with Zoom, and I was introducing you, I mentioned that you're one of the top experts in operations research, machine learning, artificial intelligence in general, and especially in the healthcare, and you gave some examples. So my question will be about this AI in healthcare to you, and it's maybe a bit provocative, but I guess many are wondering about it. So the question is, what do you think? What are your expectations? What will be happening in, say, 20 years to matters like longevity of people, the population growth, how big the population will be, and also whether there will be a danger of renaissance of eugenics and other ideas like those, and which, by the way, statisticians were also kind of thinking about, unfortunately, perhaps, and also the question of more extreme polarization when the rich who can afford AI can live perhaps much longer, much better than the rest of people. Please share your thoughts.
Yeah, I think that's again another very good question. And my own view of the matter is that, and I can tell you there are some that don't agree with me, and there are a good bunch of scholars that agree with me on this issue, is that I don't believe that that first of all, we are going to get to the situation where we are going to be worried about AI, controlling humans. I don't think that we are going to reach that anytime. There's a good book called Human Compatible that makes a great case about the fact that we're not going to get to a situation where AI controls humans. But to your question, I think in healthcare we are seeing that now AI is enabling us to discover drugs. We have orphan drugs which are very hard to discover, and these are about rare diseases that are really hard to target. But with use of AI now, we are making the clinical trials and how these drugs are being discovered much faster. So that obviously helps longevity, because now you find treatments for diseases where you could not find treatments before. And on the sort of the health disparities and on the role of AI on health disparities, I believe that we have the opportunity, and I'm seeing that AI now is being used to remove some of the health disparities that we have. So there's good stream of literature as well as ongoing work on using AI to remove disparities in healthcare rather than trying to increase it. And so I'm on the optimistic side, and I think these technologies are enabling us to make better decisions. But I understand also that at the end of the day, it depends on who gets control. Often because we are in societies that we live in, often the rich have more power than the others. So you see that Twitter is now bought by Elon Musk. So obviously the rich people can buy things and can control it, right? So I'm not denying it. But at the same time, I think that people are realizing more and more the benefits of AI and how it is helping us to resolve some sort of the bigger problems that we have, including disparity that you say, rather than increasing it. It's helping us to decrease it. And I think at the end of the day, I believe that good people will understand this, as well as the rich people who are going to buy things and control things. They're going to realize that that AI has really good advantages, and they're going to use that for improving society.
Thank you, Soroush. I agree with you, and I hope that will be indeed the case. So again, thank you very much for a great presentation.
Thanks for inviting me. Thank you.
I will pass the word to Tomohiro to conclude the event and make some concluding remarks.
Thank you.
Thank you very much for your time and insightful talk, Soroush. We really appreciate, and we learned a lot from you. And we also thank audience joining us today. And I apologize that technical issue happened in Zoom, but in the end we sorted out and then we delivered. So it's a good news for everyone. And also Soroush kindly granted us to record and circulate the recorded video after the event. After this event, after we get that video from Zoom, we circulate. And again, I want to thank Soroush and Robert and Valentin and myself. We continue this type of event so that we invite famous scholars all over the world and deliver insights from research to the society. And we appreciate your support for us. Again, thank you very much all for your time and joining us. It was a very enjoyable time for us. Thank you.
Thanks.
Have a great day, everyone. Bye.